Okay, so from Newton's second law, if this is your object, let's just start. So this is your object in that direction. So we have a tension force, and this is your thing. So from the Newton's second law, it's saying that the summation of the forces must be equal to the mass times the acceleration. So if we sum up the forces, okay, this is the acceleration towards the center. Okay, so if we sum up the forces acting up on that object, then we have that. What is the force acting up on there? So we have the tension force, which is towards the centripetal, which is now the centripetal force, is equals to okay, is equals to what? Because that is the only force it is acting, equals to the mass times the acceleration. And the acceleration here is because of the acceleration, centripetal acceleration. So it's equal to the mass times the centripetal acceleration. It is given by v squared over the r. So we are given what is what are we going to find? Is asking for the speed. Okay, so remember we have the tension times the radius squared, manipulating this equation. Divide this by the mass will give us the velocity squared. Okay, but what we want is the velocity. So the velocity is equals to, or the speed, I mean, okay, the velocity speed is equals to t times the r, which is the radius, divided by the mass of an object, square this whole thing. So we put in our things, we are given the values. So if we substitute, this is a 60 Newton. We multiply this with our radius given, 1.3, if I'm not mistaken. Okay, then we divide this with a mass given, with I can't remember what it is. Okay, which is equals to, what is the mass? The mass is equals to, I want to go up. So the mass is equals to, what is the mass? The mass, in an example here, so okay, so 0.40 kilograms. So substitute it up into that equation, then we put it up in there. Okay, so our mass, let's just put it here. We have the velocity equals to the square root, okay, tension times the radius, divide by what? Divide by this mass, then we take a square root on this thing. So it's equals to, the tension is given is 60 Newton, and then we multiply this with a radius given 1.3, and then we divide this with, it is mass of 0.4. Then we take a square root here, which gives us, like, the speed of that is equals to 4.0, I think. Just do your calculations, and then you will see something, 14 point something meter per second. So this is the velocity. So this was the velocity that this object was rotating with, as the object, as the ball, whatsoever is that one, breaks. Okay, so unless we have questions, you can ask your questions before we continue to the gravitational forces. This is the end of uniform. Do you have questions? But I'll continue to gravitational forces.
Yes, I think, Miss.
Okay, so with the gravitational forces, So we have said a bit of it. Okay, so this is just the force associated with um, gravity. Okay, but the Newton law, the Newtons have said that everything pulls on everything else. So like if you look up on this figure here, you can see that as this apple falls from the tree or wherever it came from, so you have this, that as this apple falls, as it falls, it's falling with what? It's falling with the gravitation, it's falling due to the gravitational acceleration. Okay, but now there is it discovered that the falling of the gravity, okay, so the force due to gravity, as this apple is falling, there is another force, or how will I put it? So we have the mass on this object. There is a pull which is coming up, like trying or pulling because of because it's falling due to the earth. Then you realize that because of the mass of the earth, then it also plays a role on the forces which is pulling up these objects to fall. Okay, so it's like I can say that if you have two objects, okay, so if you have two objects, okay, you have two objects. Let me say if this is an apple, falling apple, and this is an earth. Okay, so this is, let me say it's of small m, and this is of capital M. Okay, so as this object is falling, okay, it exerts a force to these objects in that direction. Let me say if this is now this one, as this one moves closer here, this object attracts, okay, let me use that, attracts that other object of that mass M towards itself. Okay, so there's a pulling force coming from this one to this one. At the same time, this one also is also now having a force on this one as it attracts this other object here. So you can say that this force is associated, okay? So the pulling force, let me say on this one, okay, the pulling force on this one, or on this capital one, due to this one, is actually, okay, so there's a mass of that capital one and the small one. So there's an attraction due to its masses. Divide this by the radius squared. But what is this thing? What caused them to attract one another? It's the gravitational constant which is between the two objects. Okay, so we have that. So we see that as this object tries to move closer, or even just standing there, okay, so it attracts another object of mass M sitting at a radius or at a certain distance. So every object pulls another object, okay, and that force or that pulling force, it's inversely okay, it's proportional to 1 over the radius squared. Okay, so you will see that, so if you increase the mass between the masses of the two objects, then the force also increases. Okay, so if you increase the radius, then if you square that radius 1 over the radius squared will also increase that force. So we'll see that what happens if you increase the radius or if you decrease the radius. Okay, so you can see that the force between the two objects, the pulling force between the two objects, is given by the gravitational constant times the mass between the two objects, divide that by the radius squared. Okay, so, and this is what we have here. So here we just have that, what is this? So we just have that the radius of, so as this Isaac the Sir Isaac Newton was doing, so he realized that everything holds onto another one, it pulls up, so that involves the distance, the masses, as I was saying, and the distances. So now that one is called the gravitation, like the tendency of pulling one another. So, and this is what we're saying. So detected this one is equal to the force is equal to values with the mass squared divided by that, not the mass, but the mass of one object times the mass of another object divided by the radius squared. So the force of gravity between them depends on the distance and of that. So, and this is just what we're explaining. So that the force between the force between the two objects depends on their distances and on their masses. Okay, so now Sir Isaac Newton's called that as the law of gravitation, or some just gives it as universe gravitation, the law of the universe gravitation, and this is what he defined, and this is just what he says there. So where that G, as I've said, is the gravitational constant, and that one has a value that as we cannot change is already given. Okay, so it's equals to 6.67 times 10 to the power of minus 11 Newton meter squared per kilogram squared. And the mass, as I said, is the mass. One is the mass 1 and mass 2. Those are the masses of the objects. And R is the distance between the two objects. Okay, so the gravitational forces of particle 1 or particle 2 to the particle 1 has the same magnitude. Okay, so the magnitude is what we were looking up on the, is what we said. So if this is an object, if you exert a force on that one, then the force on this one due to this one, okay, it's equals to the magnitude of that one. It's equals to the force, the magnitude of the force on the capital M, on that mass M due to that one. Okay, so these forces, if this is the force on that, okay, this is supposed to be the force on this capital M due to small m, and this is the force on the small one due to the capital. So we see that these forces, as you can see here, the forces in the magnitude, these forces are equal in magnitude, but they're in the opposite directions. As even you can see on this diagram, this force on this one due to this one is equals to that, and this one is in that direction. You can see that the directions, it's in the opposite directions, but the same in magnitude. Okay, so that is what we have there. Okay, now what happened when the force is falling near, it's actually near the F surface. Let's consider and say, okay, one of our objects is actually the F surface. Okay, so if we say, okay, our Earth, remember our Earth is not it's not circle, it's kind of a sphere. Okay, and then we have that our mass, it's capital M. Let me say that is the mass of the Earth is capital M. Then the magnitude of the gravitational force from the Earth to the particle of that located at that distance, it's equals to, okay, so if this is an object mass M, and we have this big one as our Earth, okay, with capital M, or let me say, just say the mass of the Earth is the mass of the particle. Okay, then the force, if these ones they are separated with the radius r, okay, then the force, okay, is equals to the force between these two on this particle due to that one is equals to the gravitational constant times the mass of the Earth times the mass, okay, remember it's always between the two particles, divide by the distance r squared. Okay, so this is the force on this object due to the Earth. Okay, and remember it's due um due to the surface. The surface is closer or near the F surface. Okay, so we have that equation. So if that particle is released and falls toward the center of the Earth, okay, remember we are saying if the particle it's moving toward the center of Earth, then the gravitational force of associated to that object is equals to what? Is equals to the weight or the gravitational acceleration. Okay, so then we have that the gravitational force, if this object is falling, okay, due to what? Due to the gravitational acceleration, then we have that the force is equals to the weight, the one it's moving with, which is equals to the what? Is equals to the mass times the gravitational acceleration. Okay, let me just say, can just say, let me just put up in the either, no problem, with the gravitational acceleration. Okay, then we will see that the force due to as it's falling, okay, if this is an object and this is the Earth, so as this object is falling towards the Earth, okay, then we have that the weight, this is the weight from that object, and we have the force between the two, okay, which is given by that, let me say this is, let me just say maybe capital M. Okay, so this is the, it's the pulling force on this one. It's, let me say it's the force, let me just say mass. Okay, so this is the gravitational force due to the what? Gravitational acceleration. So it means these two forces are equal in what? In the magnitudes. Because then we have that the forces, okay, is equals to, okay, let me just say gravitational force, it's equals to the, let me say this is the force, gravitational force, and this equals to the, to that force, okay, so you can say it's M whatsoever, okay, or can denote it with a capital G. So that means that if these two forces are equal, just in the opposite direction, then we have that the mass can equate the two equations. So the mass times the G, okay, let me just say E, equals to the gravitational constant times the mass of the Earth times the small mass, the mass of the particle, divide this by the r squared. So what do we have? We have that this mass, this is the same mass, cancels out. Then we see that over there, we left with the acceleration, okay, equals to, okay, let me just write it here, left with the acceleration, which is equals to the gravitational constant times what? The mass of the Earth, divide this by the radius squared. What does it tell us? It tells us that anything which is pulled, okay, so anything which is pulled by the if it is pulled by the Earth, okay, then we have that the mass of the the acceleration of that, the gravitational acceleration of that object, like if you said it is due to the Earth, remember we are saying that the gravitational acceleration of the Earth is equals to, okay, so this is given by the G, which is the gravitational constant, divide by the times the mass of the Earth, divided by the radius of square. So it says that anything which got pulled because of the acceleration of the Earth, then or towards the Earth, then is determined by that equation. So we have that. So we can solve that equation. We have that. So that's the acceleration of the gravity on the Earth's surface is determined by the mass of the Earth, okay, divided by the distance, okay, from the Earth. Okay, so remember, okay, this one actually the G that you're denoting is not always due to the Earth. Okay, so we can find what is the gravitational of any object. Okay, if it is situated at the, let me say, if it is a moon, then the gravity, we can determine what is the gravitational acceleration of the moon if you are on the Earth, because you know that we are given what is the distance between the Earth and the moon. Using that, we can find what is the acceleration between that, or we can make use of that also to help us to find the ratios, to find the what. By knowing all that, then we are sorted. So just note that the G, as I'm saying, it varies with the altitude. So it's like it varies with the distance above the Earth. So it differs, it's not the same. So as we previously said, that the gravitational acceleration on the Earth and the gravitational acceleration on the moon or in whatsoever is not the same. Okay, so the apparent weightless, I think you even touched more of that. Free fall, the weightless, let's say if you're falling due to the gravitational acceleration, then this is just something that we have said. Then as you go up, remember, like this one here is just tending. I think we have touched that when we were looking at the forces. So you will see that here, this one here, the normal force is equals to the weight, because this one, the lift is not moving. As you can see here, as you go up, then you can see that the lift here greater than the normal force. You will see, you get it up there. We have done this, and you see that here it's the normal force is smaller than the weight. We have done that, and here over there, because this is weightless, you are not falling. It's like the weight. Okay, so here you don't have a weight, so you're just doing there. You are nowhere falling up with that. Then you have a normal force is equals to 0. Okay, so your weight is less at the top. We have done this, okay, because you are far or further, you are far away from the center of the Earth. So we have done something like that. We have discussed about that, like depends on the altitude, depends on the normal. So that's why you are feeling, because of the further away. So you can see that if you are on the moon, your weight is lesser there. You will feel a bit less because of what? Because of the gravitational acceleration. So because of the difference in the accelerations, it's what caused the that. So unless you have questions before we move on to the Kepler's law.
Miss,
Yes.
can you please quick explain about the gravitational on Earth or something? On gravitational on the moon or something?
About the
Where
gravitational.
you actually give us, yes, where you actually give us the formula of G, and then big M, and then on the Earth, and then small m divided by R square.
Okay, okay, ours, let me say if this particle, this is a moon, okay? If this is the mass,
Mm,
this particle is the moon. Over here, we have a mass, I mean the earth, okay, of mass.
mm,
Just denote that with the mass. Um, okay, so we denote that with the mass earth. Okay, so if the distance, okay, it's always measured from the center. So the distance between them, between the moon and the earth, okay, is given by a radius r. So is this object, let me say if the moon, let me say if this is the moon and it's falling or it's moving towards the earth, the pull, okay, let me say not really moving, but the pull of gravitation, the pull of the earth, it's because of the gravitational acceleration. So it means this object, the force which is coming from the moon to that one is what? Is the weight. So it means the weight of that object is given by what? Is given by the mass of that object. In this case is the mass of the moon times what? Times the gravitational acceleration of what? Of the earth. Because the pulling, that thing, it's due to the gravitational acceleration. Okay, so it's moving with a gravitational acceleration. But also now this one, it says it exerts that force. Let's say this is the force of the gravity, the one due to this one, due to the earth to this one, okay, which is given by, that force is given by what? Is given by G, capital G, gravitational acceleration, times the mass between the two, which is the mass of the moon, times the mass of the earth, the distance, I mean, the masses of the two objects, times what? The distance squared between the two objects. Okay, so since these forces, we said that the forces are equal, just in the what? In the opposite directions. So we have that these forces are equal. So it means we have that the weight on this, the weight, that force which is coming from that to this one is equals to the gravitational acceleration of that. Okay, so then if we take, we know what our weight is. We say it is given by the mass, in this case is the mass of the moon, times what? The gravitational acceleration. Okay, equals to a G, okay, times what? The mass of the moon times the mass of the earth, divided by what? By the radius squared. Okay, the mass of the moon here is the same, it cancels out. So then we can get what is the gravitation, okay, okay, this is the, on the moon, this is not of the gas, this is the gravitational. Okay, so the pulling force is this one, so that means I can say, okay, so this, the gravity over that, it's equals to the G, the M cancels out, times the mass of the earth, divide this by the what? The radius squared. So if I find what, if I want to know what is my gravitational acceleration on the moon or on the earth, due to that, I know what is my distance, I know what is my mass. Okay, let me say if it says, okay, if you have a gravitational acceleration which is equal, if the gravitational acceleration on that object, let me say, okay, so find what is the gravitational acceleration on the moon pulled by the earth, something like that. I'll try to find more examples and I will send with you. Okay, so if we know what the mass of the earth is, like let me say the mass of the earth is equals to 20. This is not the mass of the earth, ne? Please. So mass of the earth, if it is equals to 20, I know the mass of the earth is 5 times something. So this is not the mass of the earth. And we know the radius between the moon. Okay, so the radius between the moon is equals to, say, 6 meter. The radius between the moon and the earth is 6 meter. And find what is the pull of the gravitational, find the gravitational acceleration between the moon and the earth. Okay, so using that, you can say, okay, I know what is my G. I know what my mass of the earth is, if it got pulled by the earth, and I know what is my radius squared. Okay, so I substitute what is the mass of my M, I put in the 20. I know what is my G is. My G is 6 point something times that mass of the earth, which is 20. Then I divide this with the radius squared, which is 6 meter. Then you square this. Okay, so it means the pull of the gravitational acceleration between the two is equals to that times that divided by that, which gives me, let me say, 6 or 7 meter per second squared. Okay, so knowing what is attracting what is getting attracted, knowing their masses, knowing the distances, making use of this equation, we'll be able to determine what is the gravitational or the gravitational acceleration. Okay, so what is the acceleration is it pulls with. Okay, or what is the gravitational acceleration on the moon? What is the gravitational acceleration on the planet of a mass? What is the gravitational acceleration on a what? Things like that. Okay, so please rejoin when we get disconnected so we can, I want to finish up this. We are a bit behind time. So
Okay, Miss.
did you get any questions? Did you understand that?
Miss, I got it.
Do you have any more questions or should I continue?
Maybe we should continue.
Okay, so we have done that. So now we move to the Kepler's law and motions of the planets. Okay, so most ancient cultures believe that the Earth was the center of the universe. Okay, so most felt that the planets, stars, moons, and sun revolves around the Earth. This is known as the geocentric or the phonometric universe. So as you can see here, so we believed most of the time that like the Earth is the center of everything. So everything that revolves around that, and then this was used or that was determined by this using this model, geocentric universe. So it's like the Earth is the center, and everything, the planet, moon, and whatsoever, all revolves with the Earth on the center. Okay, so the first major challenge. Okay, so this comes when Nicolaus Copernicus proposed that the planet revolves around the sun. Okay, it's like everything, including the Earth, is having the sun at the center. That is what he said here. So and everything, the planet, as it moves around with the sun at the center. And this was done by this scientist Nicolaus Copernicus, and that was long time ago in 1500 centuries. And this is what he was saying. So it's like if you have an Earth, okay, so with again what was the centric, okay, so if you have an Earth, it revolves around that with a planet mass, okay, the Earth is still at the center of the other planets, and then this one revolves around that. Okay, but later on, Kepler's used the Blahed data proposed 3 laws describing the orbits of the planets. So remember, the second one in 15th century, he said that it revolves with the what, with the sun being at the center, and then this one again said that it detailed the study of the positions. So it's like he studied again the positions of the stars and the planets in the sky over a period of many years. Okay, and then the Kepler's now came in. The guy called Johannes Kepler used that data and proposed the 3 laws of the orbits of the planets. Okay, so the first law, which is also called the law of the orbit. Okay, so he said, it says that the planets move in elliptical orbits. It's like it rotates in ellipse, okay, with the sun at one focus. So as it rotates, as it rotates, as it rotates at one focus or at one point, then we have that the orbits or the planets, whatever, either the Earth, the Mars, or whatsoever, it orbits with a sun at one focus. So as you can see here. Okay, so then he said a second law. He said that okay, as these planets are orbiting, or as they are rotating, as they are revolving, it says the line from the sun, okay, taking from one point. Now remember the first one, it's saying it orbits in the ellipse manner with the sun at one focus. So if we take that, so it's saying the line from the sun to the planets sweeps the equal, okay, the area which is equals to, okay, sweeps the equal areas of a space in equal times. So it's like if it comes at this center, okay, as if you draw a line, remember the sun is at one ellipse. So if you join the 2 lines, let's say it moves over at, okay, if the time interval is this between this point, it starts between this point and that point, then if you join the 2 areas, is what you were it's like what we were doing on the circular motions. Remember, this is moving up on the circular motions. Okay, so if you draw up the areas between, you find an area of that triangle. So if I count the area, if I count between this point, if I say this is point 1 and point 2, then the areas, okay, as it's on these points, between this point and that point, that should have the same area as I get if the point between this point and that point. Okay, so if I choose 2 different points, then the areas of those 2 triangles should be equal. So that is what the second Kepler's law says. Okay, this one is also known as the law of areas. Then Kepler's law, third law, comes in. The square of the period, the time it takes, okay, of the revolution, okay, as it revolve, or as it orbits the sun, it's proportional to the cube, okay, to the cube of the major axis. So it's like the period it takes to revolve around that sun, it's proportional to its what? To its radius. Okay,